Welcome to the deep dive. Today, we're digging into something pretty astonishing about our planet. Think about gold. Where's most of it? You might picture vaults, or maybe deep mines. But get this, over 99.999%, basically all of it is actually locked away deep underground, like 3,000 kilometers down in the Earth's molten core.
Yeah, that's right. And for ages, scientists have pretty much seen the Earth's core as this totally separate thing, a sealed vault, you could say. The idea that stuff could actually, move between the core and the layers above, highly unlikely, almost impossible, really.
Exactly. Which is why this new discovery is, frankly, mind-blowing. There's now actual evidence, solid evidence, suggesting that precious metals, including gold, are leaking out of the core into the mantle and then somehow getting all the way to the surface, like in Hawaii, of all places. It just flips that whole sealed vault idea on its head.
It absolutely does. It's a massive shift in how we think about the planet's inner workings. And we're not just talking a tiny bit of gold leaking out. This suggests our Earth is way more dynamic, more interconnected inside than we ever really gave it credit for.
Right. So our mission today, for you listening, is to unpack this. How did scientists figure this out? What clues did they follow, these tiny hints from deep, deep down? And maybe most importantly, what does this core leak actually mean for Earth's dynamics and maybe even for, the metals we rely on? We're drawing this from some great work summarized in the article, Earth's Hidden Gold, Core Leakage to Surface, which itself points to findings published in Nature.
Okay, so let's start with that core fact again. Almost all the planet's gold, platinum, things like that, they sank to the core billions of years ago when Earth formed. It's down there in that molten metal soup. An unbelievable amount of valuable stuff, just completely out of reach, or so it seemed.
Right, seemed totally locked away. But then came this volcanic clue. Researchers, these were from the University of Göttingen in Germany, they found something unexpected in volcanic rocks, specifically rocks from Hawaii. Tiny, tiny traces of a very rare metal, ruthenium.
Ah, ruthenium. And crucially, it wasn't just any ruthenium. It had a specific isotopic signature. Now, isotopes, as you probably know, are like different versions of an element. Same number of protons, different neutrons, so they have slightly different weights. What they found was more of a particular isotope, ruthenium 100, 100 Ru.
Okay, so why is that specific isotope, 100 Ru, such a smoking gun for the core?
Well, because the ruthenium that got trapped in the core way back when the Earth formed, it came from a slightly different mix of cosmic material than the stuff left in the mantle. So the core's ruthenium has this subtly different isotopic fingerprint compared to the mantle's ruthenium, specifically more 100 Ru. Finding that core-specific 100 Ru fingerprint in rocks that erupted onto the surface in Hawaii, that's like finding a message directly from the core.
Okay, that makes sense. But if these differences are so incredibly small, how do they even spot them? It sounds, technically impossible almost. Like you said, finding a specific grain of sand on a whole beach.
Yeah, it really was a challenge. For the longest time, those differences were too small to measure accurately. They were just lost in the noise. But the breakthrough here was the development of new lab procedures. Really high precision stuff, again, by the team at Göttingen. They basically found a way to zoom in on these chemical signatures like never before, sharpening the resolution, you could say, enough to finally see that tiny telltale difference in 100 Ru.
Wow. And you can imagine the moment they saw the results. There's actually a quote from Dr. Nils Messling, one of the researchers. He said, "When the first results came in, we realized that we had literally struck gold." And goes on. Our data confirmed that material from the core, including gold and other precious metals, is leaking into the Earth's mantle above. Literally struck gold, I guess, for a geochemist. That's about as literal as it gets.
Exactly. And it's so much bigger than just finding a trace of gold's cousin, ruthenium. This discovery forces us to rethink the whole interaction between the core and the mantle. That boundary down there, maybe it's not such a hard barrier after all. It implies mixing, transfer of material. It fundamentally changes the models geologists have been using for decades.
So it's not just a leak. It's evidence of a much more dynamic connection between these deep layers. What does that tell us about the Earth as a whole system?
Well, Professor Matthias Wohlbold, also from Göttingen, put it really well. He said something like, our findings not only show that the Earth's core is not as isolated as previously assumed. Okay, we got that part. But then he adds, we can now also prove that huge volumes of superheated mantle material originate at the core mantle boundary and rise to the Earth's surface to form ocean islands like Hawaii. Think about that scale. Several hundreds of quadrillion metric tons of rock. That's the stuff forming islands like Hawaii, potentially starting its journey way down at the edge of the core.
Hundreds of quadrillions of tons. That's staggering. Just hard to even visualize. Okay, so bringing it back to the surface, maybe something a bit more tangible. What about those precious metals? Gold, platinum, ruthenium. Does this core leak actually affect the supply we might find up here?
That's the really intriguing next question, isn't it? It suggests a new potential source. We know most accessible precious metals likely came from meteorite impacts after the core formed or from certain crustal processes, but this finding implies that at least some of these metals, vital for electronics, green energy, you name it, might actually be slowly seeping up from that deep core reservoir over geological time. Could this deep earth leakage be contributing, even in a small way, to the deposits we mine today? It's a fascinating possibility.
It really is. It adds a whole new dimension to where these critical resources might originate. And Dr. Messling also touched on the future implications, didn't he? He said something like, whether these processes that we observe today have also been operating in the past remains to be proven. But he concluded, our findings open up an entirely new perspective on the evolution of the inner dynamics of our home planet.
Wow.
It's like we're seeing the planet as this constantly churning, evolving system in a new way.
Exactly. It really drives home that the ground beneath our feet isn't static at all. It's the surface expression of these immense, incredibly slow but powerful processes happening deep, deep inside over billions of years. Processes we're only just beginning to glimpse.
Absolutely. So as we wrap this up, maybe something for you, the listener, to think about. This constant deep earth leakage. What could it mean long-term for how we think about resources? Especially those critical metals that are so important now. Or maybe just, how does knowing this change how you picture our planet? Not as solid rock all the way down, but this dynamic, layered, and apparently somewhat leaky sphere constantly reshaping itself from the core outwards. Definitely food for thought about the amazing planet we live on.